Okay, guys, so we are now moving on to Unit 9. And Unit 9 is our last unit. And I use the word unit very loosely because it's only 3 days of notes. It's very, very, very brief. And so we are going to do 3 days of notes. You'll do a practice day and then a quiz. And then we'll be wrapped up with all the material you need to learn prior to taking the AP test. And so Unit 9 is all about slopes. And so we are going to jump way back in time, back to Unit 2, where we talked about regression lines. And we're going to apply a lot of that knowledge today especially, but also tomorrow and the following day as well. So this is a question we have already looked at. It says, do students who sit in the front rows do better than students who sit in the back of the classroom? Here's some data recorded from a randomly selected classroom where seats were randomly assigned. So we've got the rows that a student sat in and the score that they received, let's say on a test. Is this an observational study or an experiment, and why? Well, they were randomly selected, their classroom was, but and seats were randomly assigned, so they were told where to sit. This is an experiment. So a treatment was imposed, they were assigned to a seat, and we checked to see what their score was. So this is an experiment. Because the treatment is the assigned seat. Or really it ends up being row. Right? They did not choose the row. We told them where to sit. Why is it important to randomly assign students to seats rather than letting each student choose his or her own seat? For 2 reasons. One, random assignment. Oops. Is one of the principles for experimental design. Oops. Random assignment is a principle of experimental design. Also, remember we learned about the scope of inference. It says that when random assignment is used, conclusions about cause and effect can be made. Remember, random samples, that's the population. Random assignment, that's cause and effect. How many variables are we measuring? 2, row and score. Are they categorical or quantitative? They are quantitative. Okay, what is the explanatory variable? X. That'll be the row that they are in. We are looking to see, does it explain the response variable, which is score. Okay. Now the least squares regression line, remember to do this. This is just a big review. We're going to hit stat enter. We're going to enter the rows, the x values into L1, and then the scores into L2. 1, 2, 3, 4, 5, 6 ones. 1, 2, 3, 4, 6 twos. Okay, then our scores. Okay, then once they are entered, we hit Stat, go over to Calc, option 4, Lin Reg. Make sure X list is L1, Y list is L2. Go down to Calculate and hit Enter. All right, so find that least squares regression line. It says y hat equals ax plus b negative 1.52x plus 85.95. The slope is your negative 1.52. And to interpret that, remember slope tells us the change in y for every one x. So for each additional row, score decreases by 1.52. Now think about this. So this is one sample, one-time shot look at how where a student sits affects their score. So this is one sample. It does not provide information for the whole population. Imagine that we have the whole population of all students ever, the rows they sat in, and we created the population linear regression, right? Not just for a sample, but for the entire population. That regression line would still be y hat, but we would use alpha and beta. Alpha being the population y-intercept and beta being the population slope. Alpha for this sample would be the population y-intercept. And to interpret that, it would be the score for all students when row is 0. So we could call that the starting score. Then beta, the slope for the whole population, is the change in score for each x value, which is row. Right now in our sample, it showed that your score goes down the further back you sit, right? But we don't know that for sure. Maybe this was just this sample. Maybe for the population, it would be different. We don't know. That's what beta would tell us. All right. And so remember, when we were studying linear regressions, we studied computer outputs, and that computer output gave us some information. Right? It can help us find the sample slope, the estimate for the population slope B. So this is the computer output for what we just did, right? Notice the slope is here, the constant, the y-intercept is there, right? So the sample slope here was negative 1.517. I called it 1.52. So that means score goes down by 1.517 for each row. Okay. The sample y-intercept is always next to the word constant, but under coefficient. And so that is 85.95. We called that the starting score. Okay, sometimes computer outputs give us the standard deviation of the residuals. That would be written as S. In this case, it's not provided. But remember that that S is the estimate for the standard deviation of the population. It is the amount that predicted or predictions are off by. Right? And so remember, if that standard deviation is really big, then our regression is not very good because it's got really high error rate. But if it's small, then our prediction is pretty consistent and it's got a pretty low error rate. The last thing we know is the standard error of the slope. So if we go here to the slope, notice right next to it is SE coefficient. That's the standard error. It's the amount by which our sample value varies from the population value. So in this case, our sample slope varies from the population slope by 1.332. Okay, so to interpret that, we would say the sample slope varies from the population slope by 1.332. Now that tells us no matter what, this population slope is going to be negative, right? Because if we even added 1.332 to our negative 1.517, we would still be in the negative. So that sort of gives us evidence that no matter what, the further back you sit, the lower your score will get. It just depends, or I guess what changes is how much lower your score is going to get. So again, as we know, one sample provides us with a point estimate for a parameter, right? Point estimate, just one point in time. In the past, we learned that confidence intervals help us to estimate for a population parameter. So if we don't know the value of beta, the population slope, we're going to learn how to do a confidence interval for that beta value, that population slope. All right. Now, for this confidence interval, we have a lot of conditions that we have to check off. And we use the acronym LINER. It's not linear, it's LINER. Right? The first one is linear. It says the actual relationship between X and Y is linear. This requires a scatter plot. Right? So we can only say we have a linear pattern if we can see that pattern on a scatter plot. The second is independent. This is just the 10% condition. The third is normal. For any fixed value of X, the response variable Y varies according to a random distribution. What does that mean? It means that we have to have a stem plot or a histogram of the residuals to be sure that they are not skewed and that they look relatively normal. Okay, so to check off normal, in this case, we need either a histogram or stem plot of the residuals. That's really important. E stands for equal standard deviation. The standard deviation of Y is the same for all values of X. This requires a residual plot to be sure that the vertical spread of the residuals is similar for all X values in the data set. All right, so you have to have equal spread of residuals, both positive and negative. That's your vertical spread, positives and negatives. And then the last one, random. The data are produced from a random sample. So we know independent, we know random, those are easy. Then linear requires a scatter plot of the data. Normal requires a stem plot or histogram of the residuals to make sure your residuals are symmetric and normally distributed, let's say. And then E, equal standard deviation. We have to be sure that our residuals are balanced vertically. All right, so here's an example. There is a link between the amount of cigarette smoking in countries and death rates from coronary heart disease. Below is the computer output from a regression analysis of this relationship for 14 randomly selected countries from around the world, along with a residual plot. The explanatory variable is annual consumption of cigarettes per person, and the response variable is annual deaths from CHD per 100,000 people. All right, so we are given a residual plot, all right, and we're given our computer output. So write the least squares regression equation, y hat equals, remember constant, coefficient, those are our slope and y-intercept. So our slope is 0.02268x plus our y-intercept 65.44. Identify and interpret the estimate for the population slope, 0.02268. To interpret that, we would say for each X was the explanatory variable. It's the annual consumption of cigarettes per person. So for each cigarette, per person, coronary heart disease deaths increase by 0.02268 per 100,000 people. All right, so remember, slope is the change in y for every one x. Identify and interpret the population y-intercept. This is our 65. All right, and that means when cigarette consumption is 0, deaths from coronary heart disease are 65.44. All right, the standard deviation for the population, that's always your S value, 45.2672, tells us that on average, the predicted values for y, so predicted number of deaths is off by 42.2672. Those are all three things you learned back in Unit 2. This is the last one. The standard error for the sample slope is this guy, 0.01926. And it tells us the sample slope is 0.01926 off from the population slope. And that's an average. Right, we don't know it's exactly that much off, but it's on average that far off. Based on the information given, discuss whether the conditions have been met to use the T procedures to make inferences about the slope of the regression line. Can we do a confidence interval? All right, well, this is the L, I, N, E, and R. Okay, so linear. Do we have a scatter plot of the data? We do not. So we cannot say, because we do not have a scatter plot. Okay, I, independent. Here we took a sample of 14 countries around the world. 14 is definitely less than 10% of all countries. So we are good there. N for normal. Do we have a scatter plot or not a scatter plot? I'm sorry, normal. We need a stem plot or a histogram of the residuals. We do not. We just have a residual plot. So we do not have a stem plot. Oh my goodness. Or a histogram of the residuals. So we can't say that it looks normal because we don't have it. All right, no, E, equal distance. So remember, your residuals for E have to have a residual plot, which we have, that shows the vertical spread of the residuals is similar for all X values. So this, all of these are balanced, right? And that is true because in this case, we've got a variety of vertical distances where we've got both positives and negatives. So they are balanced out. Okay, so vertical spread of the residuals is balanced. Now, let's say we had a lot on the bottom in the negatives and very few on the top, then we couldn't check that off. We clearly have way more negative residuals than positives. And then R, random, 14 randomly selected countries. Yep. Okay, notice there are 5 conditions. So it is hard to have enough information to check off all 5. And so you can see in this example, we couldn't because we don't know L and we don't know N. We can't check those off. All right, so tomorrow we will move forward with how to calculate those confidence intervals. For the beta value for the slope, and remember the whole goal there is to find the population slope. So if we could sample every country and run a linear regression, what would the slope be? That's what we're attempting to estimate. All right, you've got an exit ticket. Let's see what you can do, and we'll talk to you tomorrow.